Weights initialization is crucial in training neural networks. It sets the starting point for optimization algorithm. The activation function applies a nonlinear transformation for a neural network. Different activation functions serve different purposes. Choosing the right weight and activation function is key to better neural network performance. Xavier initialization is ideal for sigmoid and tanh in feed-forward networks. He initialization pairs well with ReLU for faster convergence, especially in convolutional neural networks. Matching the initialization method and activation function improves training efficiency and model performance. Gaussian or normal initialization draws weights from a normal distribution. The concept of Gaussian initialization has its roots in the early studies of neural networks. The weights W are initialized using a normal distribution defined as W. You can see this strange N mass symbol, and we have arguments which represents a normal distribution with mean 0 and variance sigma squared. We can implement a normal distribution without any problems with NumPy and with Python. Let's first of all import the NumPy and pyplot. Then I want to install the numpy.random seed. Let's set up like 96. It's just for reproducibility of the results. And now we need to create two variables: input size and output size. Let's use 2 and 256. Okay, and now we need to create a variable weights normal. Let's call numpy.random.randn, and we need to put input size and the output size. Okay, good. We can check the shape of this matrix. Let's run this cell, and I can see that this is just 2 times 256 items matrix. Now let's plot a histogram of the weights, and I just want to use this magic trick. Yeah, and we just flatten the weights normal. Yeah, we use, instead of the matrix, we draw a vector. We use 30 bins for the histogram. Yeah, let's run this code. And you can see the histogram of Gaussian initialization. Yeah, it's just the standard bell-shaped curve. And in practice, Gaussian initialization is often implemented as a variant of Xavier initialization, where the weights are draws from a normal distribution scaled by the input dimension. And the Xavier initialization looks like this. It's the standard normal distribution with mean 0 and variance 1 over number the input neurons. If you wanted to know more details where the range of Xavier uniform initialization comes from, you can check my blog, links under the video. So, and Xavier initialization works particularly well with sigmoid and tanh activation functions because it helps to prevent saturation. And now let's make a Python implementation. By the same way, let's install the random seed and install the input and output size variables. First of all, let's generate the normal distribution. We can copy this code and paste it right over here, and we need to rescale our standard normal distribution by this scalar square root of 1 over the number in. It's just change this scalar just changes the variance of our standard distribution to the desired one. Again, you can check my blog for the details how this works. And now we can create weights Xavier, and we need to multiply n times the NumPy square root of, and we have square root of 1 over the number of input, or the input size variable. We can use float, 1.0 over the input size. And now by the same way, let's plot a histogram. And you can see how it looks, it's pretty similar with the previous result, but it's a little bit more narrow, It's tighter than the standard normal distribution. Let's compare, let's just compare this one and this one. Just wanted to put it closer, And now it's obvious that the Xavier initialization little bit more narrow, it's very tight near this 0 area. That's just because we rescale the variance of the normal distribution, of course. And in modern deep learning practice, Gaussian initialization with Xavier scaling has become the de facto standard due to its robust performance across different architectures and tasks. Okay, and He-init uses the normal distribution with mean 0 and variance 2 over number of input neurons, and by the same way as before, we need to use multiplier the square root of the variance, because we scales the standard deviation to match the He initialization rule, If you want to know more about this scalar and why we have square root, just look at my blog. Now let's implement this initialization. I can copy this code and paste it right over here. Okay, we have the same part of the seed input and output. We have the same normal distribution, but instead of this scalar, we have 2 over the input size. And right now, it's not the Xavier, it's He initialization. Okay, and now let's fix the plot. Okay, and you can see how it looks, He initialization shows a slightly wider distribution than Xavier. Let's compare with the Xavier, You can see that really He initialization little bit more wider. This increased variance compensates for the ReLU activation function's tendency to zero out negative values, We just switch to 0 all the negative values when we use the ReLU function, The He initialization can be further adapted for Leaky ReLU activation function. For Leaky ReLU defined as this, function, the initialization is modified to this normal distribution with 0 mean and 2 over the 1 plus alpha squared times the number of input neurons parameter. So, and alpha is the negative slope parameter of Leaky ReLU, and typically it's 0.01. So we can use this square root scalar, by the same way as before, and make an implementation of this initialization method. And here we go. Compared to the He initialization, we need to add one more parameter, alpha. And then we generate normal distribution, and He initialization looks like this. We just use a new scalar. And you can see that when alpha equals 0, this reduces to standard He initialization, because we just destroy this term. And for typical Leaky ReLU with alpha equals 0.01, the difference from the standard He initialization is minimal. But when this alpha become more significant, the difference is more and more obvious. And I have one more plot, and I built this for initialization and then visualized them side by side. And you can see that random normal initialization shows the widest spread of weights with no consideration for the network architecture. This can lead to vanishing or exploding gradients, especially in deep networks. And Xavier initialization, it's a more controlled distribution with weights scaled according to the input dimension. This can prevent this vanishing or exploding gradient, especially for sigmoid or tanh activation function, because this narrowed spread helps maintain stable gradients when using sigmoid or tanh activation functions. He initialization, it's just a blue plot. Shows a slightly wider distribution than Xavier, but still maintains a structured spread. This increased variance compensates for the ReLU activation function's tendency. When we just in negative diapason, ReLU just zero out the negative values. And the last one, it's Leaky He initialization, and it scales the variance for leaky ReLU activations, slightly narrowing the spread compared to the He initialization. But right now we have a very small slope alpha, it's standard 0.01. It can ensuring the effective propagation of both positive and negative signals, yeah, in the case of leaky ReLU, because we have no this zero out negative values for the leaky ReLU because this alpha slope turn. Now let's create a code for the universal weights initialization. And first of all, let's define the function parameter. And we have the input size. Let's init it as integer. We have output size as the integer. And we have the init method. And we can use the literal from the typing package, yeah, and we just install the Xavier, He, Leaky, normal and uniform distributions for our initialization. And by default we use Xavier initialization. And let's add two more parameters, gain and alpha. So we return the numpy.nd array as the result. Okay, good. Okay, and we need to initialize the normal distribution all the time, yeah, because most of this initialization method just manipulate with the scalars of the random normal distribution. So we have this normal distribution as numpy random rand n, put input size and output size to the parameter of the random distribution. And now let's check our init method. If the init method equals to Xavier, we need to create a standard deviation or the multiplier for the normal distribution. Let's recall this Xavier multiplier, yeah. Let's create here variable standard deviation std. We have this Xavier multiplier and let's multiply it by the gain. So we want to gain our initialization, yeah, and in case if you wanted to make it stronger or softer. And we need to return the normal distribution times, or let's say standard deviation times this normal distribution. And for the next step, let's do the same for the He initialization. Okay, but we need to use different standard deviation. So we need to multiply gain times 2 times to the square root of 2 over the input size, and I think that it works for He. And let's implement the same logic for He Leaky. We need to Leaky He init multiply this scalar. Yeah. Okay, I think that it works fine. Okay, now let's make for the normal distribution. We need to return the normal distribution times the gain, yeah. I don't think that we need any multipliers, yeah. And for the uniform distribution, we need to multiply gain times to the uniform distribution in range between -1 and 1. And we provide the size as the tuple. And in case if we just didn't match with any of this method, we need to raise a value error that we have no any idea what kind of initialization method we need to apply. Also, we can create a class parameter with similar signature in the initialization, in constructor of this class. We need to have input size, output size, and gain. So then we need to install to the self the input size. Same for the output size and for the gain. And then let's define methods. For example, let's start from the he. We have self as the argument. We need to return the parameter and as the bunch of the arguments, we need to provide self input size, self output size. Then we need to install the initialization method. We use he, and I think that it should work. Yeah. The last one, yeah, it's gain, of course. We need to install self gain. Okay, good. Also, we can create now the he Leaky. We need to install the he Leaky initialization. We can create the Xavier method. We need to install the Xavier right over here. Okay, and now we need to install normal and uniform. Let's do the same copy paste magic, yeah? Normal and the uniform. Okay, now let's run this code. It works, yeah, it works. And I have one little example for you, yeah? For example, we have input size 1, output size 10, and gain 0.1. We use he initialization, and here we go, yeah? Right over here we have a bunch of weights that we can use for our model. While batch normalization has made weights initialization less critical, it's still important. Batch normalization normalizes layer inputs, reducing the effects of poor initialization. Even so, starting with proper methods like Xavier or he can improve convergence speed. Combining good initialization with batch normalization gives the best results for training deep networks.